Velocity stacks. What are they? When do we need them? And what do they actually do? Here we go. All right, so let's get started by taking a look at the CAD. What we have here is an induction tube. We have a little green portion here. This is going to serve as our velocity stack for this example. Nice little air filter we have on there, a little conical guy. And then around that is a shroud. And this, think of it as an air box. It's just going to simplify the CFD a little bit so that we can do an internal flow, which requires a lot less calculation. So to get started, let's go ahead and take a look at the front view. Cut this bad boy in half. Let's take a look at what we have here. So we're going to be looking at two configurations in this example. Here, obviously, we just have a hole coming in behind the air filter. Nothing fancy, just squared off. And this is going to be essentially the worst case scenario. I'll switch over here to my other configuration. And what this does is applies a fillet to this geometry. This is going to serve as our velocity stack. And so what is a velocity stack? It's a really fancy term for fancy fillet. There's a ton of literature out there you can research on what is the best geometry and how to optimize it and get the most flow that you possibly can. But for all intents and purposes, it's a fancy fillet. It's going to just have varying geometry throughout it. If we look close here, this one was actually created using a spline, so it's not exactly a circular fillet, but it serves the point. I didn't really spend a lot of time optimizing this. I just kind of put it together knowing that this is going to serve the purpose. So let's go ahead and get to it. I'll set this back to our normal setup and we will start looking at some CFD. All right, so we got the CFD open. Let's take a look at the conditions that we're using to get this thing running. I'm going to go ahead and do another cross section here just for simplicity. So let's talk about how we're going to induce flow. So this is going to be done through a pressure differential, and essentially what's happening here is this little red surface on the back. I'm assigning a static pressure to that. In this particular case, about 10 psi. And the blue portion, that's going to be our inlet. That's where we're going to have an environmental pressure, which is essentially your atmospheric pressure, about 14.7. The next part is going to be the media filter. For this, on the air filter, all I did was assign a porous media. Just came up with something that's going to give me a pressure differential. And if we wanted to, we could inject particles and you could actually see how it would filter some of that stuff out. But it's a really efficient way to represent a solid media that air can pass through. And then for a goal in here, this isn't really relevant, but I just assigned a mass flow rate for something for it to use as a condition to solve for. So that sums that up. Now we can start looking at the results. I'm going to go ahead and open this guy up. And let's take a look at this first section here. All right, so let's start off by looking at pressure so we can get an idea of the actual pressure differential we're working with. I'm going to go ahead and change this. I have it at static pressure right now. Let's go ahead and look at relative pressure. That'll be a little bit more easy to understand in the terms of what you're actually experiencing. So I'm going to go ahead and grab my little tool here, and we'll take a look at this pressure and this pressure. And we can see from that we have a relative pressure of about minus 4.7, and as you would expect, this is going to be about 0. So when I say relative, this is relative to the atmospheric pressure. So we can see in this case we got about 4.5 inches, or psi, excuse me, of vacuum in this particular scenario. So that's going to drive this flow. Now, for what it's worth, and any of you who understand this, 4.5 psi is pretty substantial amount of vacuum, probably something that would only be induced with a big power adder, probably like a turbocharger or a supercharger or something like that that can really generate a lot of flow. Of course, it's going to be dependent on your intake tube and stuff like that. But let's dive into this a little bit deeper here. So we can see the air coming in, going through our filter, getting a little pressure drop there. And we notice we're getting this transition here into the intake tube. And the big takeaway, initial inspection says, hey, we got some vortices going on here. I like to call these whirly bits. I think whirly bits is a much better term than a vortex. But you can decide for yourself. So let's go ahead and switch over to our actual velocity stack and see what that looks like. All right, we'll go ahead and put this back to relative pressure so we're looking at the same thing. Great. Okay, so same idea, about the same pressure differential here, but we notice we have not so many whirly bits in this section here. A little bit smoother transition for the pressure, and so that's definitely ideal. So what should we look at next? I think it might be relevant to, well, okay, this looks nice. What does that actually mean? Let's go ahead and I'm going to hide you, and let's look at actual flow rates. So what we have here is I've set up where the air is coming into the high vacuum portion of this. We're going to look at average velocities and volumetric flow rates. So we're seeing here we got about 2,683 cubic feet per minute. That's a pretty good flow rate. So if we go back to our other guy, let's go ahead and open up that same parameter, and we're seeing about 2577. So there's a bit of a difference there. Let's go ahead. I'll tell you what. I'm going to go ahead and chart this. I'm going to look at a few other scenarios in here as well. We're going to look at a little bit lower vacuum, and then something that might represent more like, rather than having this big, huge power adder that's going to create all this vacuum, maybe something more of like a naturally aspirated application where instead of this, we're looking at about 5 psi here, a little bit closer to maybe in the 1 psi range. And then let's look at a very low vacuum, so something maybe like if you're just driving down the road. Not such an extreme scenario to see, what this velocity stack is doing for, more of that everyday condition. So let me go ahead and take care of that, and I'll get back to you. All right, well, the results are in. I've got all that run, tabulated, and put into a nice table form here for everyone. So let's take a look. Let's start here at the top. So this dP, delta P, this is our pressure differential. So I've got 3 different scenarios here. This is our very low delta P scenario, kind of our one here in the middle, more the let's call it naturally aspirated, and then we got this big guy here that's creating a lot of flow. This is the one we looked at here initially, so let's just start with the results in that. These were the 2 volumetric flow rates that I showed you on the where the air is coming out of the filter, or after it's exiting the velocity stack. And that's showing us a pretty nice little gain here of about 4% increase in the volumetric flow rate. So that's a nice little gain. So what happens when this pressure differential is not so extreme? Well, we still get some increases here. We still have a nice little gain, a little, let's call it 2.5%, maybe a little bit less. And then when we go down to this much smaller pressure differential, well, we certainly still see a gain. Is it significant? Probably not, and certainly might be in the noise of the statistics of the CFD, but it's certainly not a loss. The other thing that is pretty noteworthy here is the average velocity. So this is the velocity of the air coming out at that same measurement location, and obviously this is kind of exponential, just like our pressure differential. So we would expect that. When do we need to use a velocity stack? When I look at this and I kind of break it down, it really depends on what you're going for. If you're chasing every last little bit that there is to be offered from your intake system on your car, it's never a bad idea. It's always going to show you some sort of gain. So if you're out there and you're chasing, fractions, it, use it. There's no downside to using this from a flow perspective. But if you're going to have to work hard to make it fit, or you're going to actually have to fabricate this yourself, and you're wondering, is it worth my time? One thing I would say is, if I had to pick a point, this looks like a nice number here. It's about 100 feet per second. So what you could do is go through and kind of estimate how much airflow is going through your engine, and look at the cross-sectional area of your intake tube and get an idea of what this air velocity is going to be on average. And then use this as a gauge. And if you're definitely looking over at 100 feet per second, this is definitely something you might want to look into. But, if you're down here, you got this huge intake tube, and to make a velocity stack fit on the end of that tube is going to be a pain in the butt. There might not be anything there for you. A little bit more problem than it's worth. But ultimately, you have to be the decider of that. So I think the next thing to talk about here is going to be why. Why do we see these gains? Let's dive into what's going on there a little bit. We've already kind of seen the whirly bits and what they're doing, but let's dive into what that looks like a little bit deeper, to maybe get a better understanding of what's going on here. All right, so let's talk about velocity. On the top of the picture here, what we have is the one with the radius velocity stack, and then the lower one is obviously without. So what do we notice? There's a few things to take away from this. If we look at the throat where the velocity stack is, bringing the air in, we notice a lot smoother of a transition. So if we look at the velocities on near the sidewalls going towards the center, we see a velocity that is up in that 470 feet per second range, versus when we go to the one without the velocity stack or the fillet, we're almost stagnant there. And in fact, that's because of the whirly bits. We really are essentially stagnant. And then if you look at the velocities as it goes down the tube, there's a much more significant gradient from the sidewall to the center of the tube. And so that's never a good thing. What we really want to strive for here is having the closest thing to the same velocity throughout the entire tube as possible. So if we look at the outlet there at the end where the surface parameters are labeled, the very top parameter is velocity average. And what we notice here is that the velocity is actually higher on the tube with the velocity stack, which makes sense. We're flowing more air, we have the same cross-sectional area, we're going to have a higher average velocity. But what's interesting is if you look at the maximum velocity there with the little red tag, we're actually considerably slower for maximum velocity when compared to the tube without the velocity stack. And notice that the locations are different. So in the one without the velocity stack, we're actually getting our maximum velocities in the throat where that air is all converging together. But because we don't have as uniform distribution, what's really happening there is we're starting to choke down, and effectively, have a smaller area that the air is actually passing through. Okay, so that leads us into talking about the pressures. So this is basically the same thing, but zoomed in a little bit, and we're looking at relative pressures again. What you're going to notice here is looking at the throat where the air is all coming together, as you would expect, because it had a much more uniform velocity with the velocity stack going across from the wall to the center of the throat. The pressure is a lot more uniform as well. And then there at the bottom, I have highlighted the area where you're seeing a lot of this turbulence. So up to this point, we've been talking a lot about vortices and or whirly bits, as I call them, and how they're really impacting the flow here. So let's talk a little bit about vortices and whether they're good, they're bad, they're friend, they're foe. It really depends on what we're talking about. A couple general rules of thumb if you're talking about internal flow, so inside of this tube or inside of an intake manifold or something like that, they're typically not going to be doing you any favors. An exception to that might be is if you're trying to get a mixing action going on where you're trying to get two different things to become homogeneous. Then they can be your friend. But typically, if you're concerned about flow rates, they're not doing you any favors. Now, if we're talking about external flow, so if you think about air going over a car, there's a lot of examples where vortex generators can do you a lot of favors. A good example is the canards on the front of a car. These create massive vortices. If you think of a Formula One car in the front wing, massive vortices coming off these things, and you can use those to your advantage. A more commonplace example that you might be familiar with would be like a golf ball. Those little dimples, they generate what the fancy people call are eddy currents, but they're whirly bits. They're really whirly bits. Eddy currents is a term used by really, people who drink lemon drop martinis, and they have their fingers up in the air while doing so. But anyways, back to the whirly bits. So they can be your friend or foe. And this is such a common phenomenon that we actually have a parameter that we can look at within SolidWorks that's, directly measures vortices. So let's go ahead and take a look at that. I'm going to do it right here in the CAD itself rather than showing you a picture. So what I need to do is open this up. We'll go ahead and show. We're going to do this cross section here. This is the parameter, vortice, makes sense. And what we need to do is determine a maximum value. If we open this up to like the global maximum, you're really not going to see much. It's going to basically pick the highest value there is and then adjust the scale for that. And that's not telling us a lot. So what we need to do is kind of back this down to a point where we get something that we feel is visually useful. And what I kind of have determined for this particular flow rate is about 15,000 seems like to be a pretty reasonable number. And what we can see here is, these are those vortices that are choking down the flow rate. You can see how they extend right off that sharp edge. If we zoom way in here, you can actually see how the turbulence is taking over and then basically creating this massive boundary layer, essentially restricting that flow. So let's bounce over to our other project here where we got the actual velocity stack. And if we use that same value, we can see that those numbers are drastically reduced. That the region that's affected by that is very insignificant, but it is still here. If we zoom in on this a little bit more, we don't see the turbulence necessarily at least in the flow lines, but because we are still seeing that higher number there, this would definitely tell me that we could probably optimize this geometry a little bit better and maybe get a little bit more flow out of it. And this is the tool that I would probably use for going through and optimizing that geometry. So with that being said, this is a really neat way to analyze that, but it limits us to the 2D realm of things. And one thing that we can do is actually look at this in a 3D type of environment. And this is where the ISO surfaces come in. And what this does is essentially looks at those same parameters, but then applies it three-dimensionally so that we can get a little broader understanding of what that actually is. So one of the things I'm going to pull up here is going to be, I have a pre-made picture for this. And what we have here on the left is the velocity stack. The one here on the right is without the velocity stack. And we are looking at those same vortices with those same upper limits. And if we wanted to, we could go through and we could change, the coloring on this and do all kinds of fancy stuff to get a little bit better idea. But the takeaway here is how much that region is minimized by adding that velocity stack. And that's really what's going to be driving the reduction in flow rate when you don't have that velocity stack in there. And so the end goal here is to actually minimize this to as far as possible. Obviously, I haven't done that here in this design, but we're certainly getting close. We've made a big improvement. And the takeaway from the earlier results that we talked about in the table was how this is very proportional to velocity. So if you are constricted and you can only run a really small intake tube because of how it packages, this is where you're going to see the benefits of this type of thing. So I hope that is helpful. All right, so what have we learned? Well, essentially that velocity stacks are definitely a good thing, especially when you're running really high flow rates. But I know what you're thinking, like this is probably kind of complicated. For some people, you're not going to have access to all this fancy stuff to come up with this perfectly optimized fillet and, figure out if it's working or not. So let's look at something here like a total hack job. I don't have a lot of options and I'm just going to do something really simple. Let's go ahead. I came up with this guy and it's just a chamfer. It's nothing fancy. It's a 45-degree chamfer. You could seriously just get out a file and go at this thing and, end up with this. What's this going to do? Is this going to hurt our flow? Is this going to mess up things up so bad? Well, let's take a look. Let's go ahead and get this guy loaded up. All right. What do we think? We're going to take any bets here on how this is going to look? Let me go ahead and get a nice front-facing view. Well, this is total pressure. Let's go ahead and look at vortices, just because that's what we were last looking at. Oh, good. We're already set to 1500. Well, is it as good as the fillet? No. But I don't see any massive... There's a little turbulence in there, like actual flow lines shifting around. And we do have a little bit more red region in the vortices, but let's take a look at some actual numbers. So how bad is this? Let's look at our flow rate numbers that we looked at last time. Let me see, how do I pull this up? I've done this before, I promise. All right. So 2645. Now, if I remember right, that's not too far off from what we had. Let's pull it back up our fillet here. So 2683. That's not terrible. That's a substantial improvement over no fillet at all. And it's kind of a hack job implementation. Is it as good as the fillet? No. But that's interesting. So for you guys looking for a simple, easy solution to maybe get a little bit extra flow without putting in a lot of R&D, that might be a good option for you. I'll have to think about that a little bit more. Okay, so that brings us to the end. What did we learn here? Well, anytime you can add a radius or even a chamfer to an area like this where you have to transition into a tube or out of, this also applies to coming out of a tube. This is never a bad thing if you have the capability, the room, and the just overall ability to do it. If you're not trying to pinch and get every last little bit out of it, let's look at those velocities, and if we're around that 100 feet per second, then maybe it's something really worth pursuing. So I hope that was useful. A lot of fun doing this, kind of informative. I'm really surprised about the chamfer. So take it easy until next time.